Hello, my name is Taemin Park and I will introduce our research. With the help of benchmark datasets that contain a large amount of labeled data, classification algorithms based on deep learning have made remarkable progress. However, in many real-world datasets, the number of unlabeled samples far exceeds the number of labeled ones. In such cases, training a deep classification algorithm with only a small amount of labeled data often leads to overfitting. To address this, many semi-supervised learning or SSL algorithms have been studied. They leverage unlabeled data together with labeled data to improve classification performance. While SSL algorithms have been effective, they usually rely on an assumption that is often unrealistic in real-world scenarios. They assume that the training set is class balanced, meaning each class contains the same number of samples. In practice, training sets are often imbalanced between labeled and unlabeled data. For example, hospitals usually have more data from healthy patients than from those with rare diseases, and factories collect far more data under normal conditions than during floods. When trained on such data, SSL algorithms become biased toward major classes. This problem is even worse with store labeling, since biased predictions on unlabeled samples create biased labels, which then reinforce the bias. As shown in the confusion matrix on the right, binary classes such as 8 and 9 are often misclassified as majority classes like 0 and 1. In real applications, this means diseases may go undetected in hospitals or faults may be missed in factories. Therefore, we need class imbalanced semi-supervised learning algorithms that can still detect minority classes effectively. Before introducing CISSL, let me briefly review real related studies. First, CISSL is closely related to general SSL research. Many SSL methods are based on three key techniques: entropy minimization using store labels, mix-up regularization through interpolation, and consistency regularization that enforces stable predictions under data augmentation. All three aim to place the classifier's decision boundaries in low-density regions, as illustrated on the right. Recent SSL algorithms combine these techniques to achieve stronger performance. In CISSL research, fixed match and remix match are commonly used as the base SSL algorithms, so I'll explain them in more detail. Fixed match and remix match are relatively recent SSL algorithms that enhance consistency regularization using strong data augmentation. For example, on rival samples, they generate two versions, a weakly augmented one and a strongly augmented one. The weakly augmented prediction is used as a store label, and consistency between the store label and the strongly augmented prediction defines the unlabeled loss. Fixed match further adds a classification loss on weakly augmented label samples, while remix match additionally applies mix-up regularization with store labels. These methods work effectively on balanced datasets, but as mentioned earlier, they suffer from strong bias toward majority classes under imbalanced training sets. The experimental setting is as follows. We have a labeled set with n labeled samples and an unlabeled set with m unlabeled samples. For each class, we denote the number of labeled samples as nk and the number of unlabeled samples as mk. We sort the classes in decreasing order of labeled sample size and define the imbalance ratio of the label set and gamma L is the ratio between the largest and smallest nk. Similarly, the imbalance ratio of the unlabeled set gamma U is defined in the same way. In this work, we assume that the class distribution of the label set is unknown and may even be mismatched with the label set. During training, we sample mini batches from both labeled and unlabeled sets in each iteration and train a classifier F to predict test set labels. We denote the logits of F as G. The proposed algorithm The proposed algorithm LLA learns how much to adjust the logits by leveraging both labeled and unlabeled sets. Specifically, we introduce the class-specific adjustment parameter that determines the degree of logit adjustment for each class. These parameters are optimized by minimizing a class average loss defined over both labeled and unlabeled set data. Once trained, they are used to refine the storables of the base SSL algorithm, as well as the class predictions on test samples, thereby mitigating classifier bias. In addition, NLA also addresses representation imbalance. As mentioned earlier, binary class A samples tend to form sparse clusters in the representation space, making them harder to distinguish. To overcome this, we extend the concept of feature cluster compression, originally proposed for class imbalanced learning, into the context of CISSL, encouraging binary class features to form denser and more separable clusters. Let me now explain our proposed algorithm in more detail. First, we compute the logits of weakly augmented label samples using the base SLR algorithm. These logits are then adjusted by the class-specific adjustment parameters currently being trained. Next, we calculate the class average loss for the label set. This loss is simply the average of per-class losses, where each class contributes equally regardless of the number of samples in the mini-batch. Because of this equal weighting, minimizing the loss prevents the adjusted losses from being biased towards specific classes. As a result, the adjustment parameters are naturally optimized in the desired direction during training. Similarly, our algorithm uses unlabeled samples to learn the adjustment parameter by computing a class average loss for the unlabeled mini-batch. First, we compute the logits for strongly augmented unlabeled samples and adjust them using the current adjustment parameters. We then calculate a class average loss in a similar way as for labeled data. The difference is that since we do not know the true labels for unlabeled samples, we use two labels instead of the true labels. While this loss may look similar to a reweighted loss, there is an important distinction. Reweighted loss requires the class distribution of the entire dataset, whereas the class average loss is computed using only the predicted label proportions with the mini-batch. This allows us to optimize the adjustment parameters without knowing the class distribution of unlabeled set. By combining two class average losses I just described, we obtain the overall class average loss. The proposed algorithm trains the base SSR algorithm and the adjustment parameters end-to-end. During training, the base SSR algorithm uses the storables refined by the adjustment parameters. The overall training loss is simply the sum of the base SSR training loss and the overall class average loss. At each iteration, we minimize this loss to update both the base SSR model and the adjustment parameters. To summarize the process with the figure, the base SSR algorithm computes logits for both labeled and unlabeled mini batches, which are then adjusted by the adjustment parameters. The adjusted logits are used to compute the class average loss, and the refined storables are also used in the base SSL loss. During the test phase, the adjustment parameters are applied to refine the class predictions for test samples in the same manner. As mentioned earlier, our proposed algorithm extends FCC, a method from the class imbalanced learning field, to also address imbalance in the representation space. Let me first explain FCC. FCC ensures that binary class samples from denser clusters in the representation space by modifying how features are fed into the classifier during training. Instead of passing CNN-extracted features directly to the classifier, each feature is multiplied by a class-specific scaling factor. In the original FCC, the scaling factor gradually decreases from majority to minority classes. By applying larger scaling factors to majority class features, the classifier is trained such that minority classes features do not overlap with expanded majority features, encouraging minority features to occupy denser regions. Importantly, this scaling is applied only during training. Then during testing, features are used as is to leverage the learned dense clusters. While FCC improves performance in fully supervised class imbalanced learning, it has limitations in the CISL setting. The original scaling factors are calculated solely based on class index and do not incorporate the unlabeled set classes distribution, which can reduce classification performance. Therefore, we extend FCC to better fit the CISL context. Let me now explain the extended FCC, which adapts FCC to the CISL context. The key idea is AFCC is to reuse the lambda parameters which are learned from both labeled and unlabeled sets so that the class distribution of both sets are incorporated. For label samples, FCC works similarly to FCC. The extracted features are multiplied by a scaling factor before being fed to the classifier. Unlike FCC, however, the scaling factor is determined using lambda, so the classes with larger lambda receive a larger scaling factor, while classes with smaller lambda receive a smaller one. Since we are in a CISSL setting, we also apply scaling factors when computing logits for unlabeled samples. Because the labels of unlabeled samples are unknown, we calculate the final scaling factor using soft store labels and a per class value, tau k for each class. This allows the FCC to appropriately scale features for unlabeled samples as well. We conducted to evaluate the classification performance of our proposed algorithm. In this slide, we show results on Cypher10 LT under a setting where the class distribution of labeled and unlabeled sets are the same. The proposed algorithm outperforms our baseline method across all settings. These results demonstrate that our method works effectively even when the class distribution of the labeled and unlabeled sets are matched. Next, we conducted experiments on Cypher10LT and STR10LT under settings where the class distributions of labeled and unlabeled sets are different. The results showed that our proposed algorithm consistently outperforms our baseline methods. This is because it learns how much to adjust the logits while considering the class distribution of those labeled and unlabeled sets, effectively rebalancing the classifier. In addition, unlike other methods, it also mitigates class imbalance in the representation space. More experimental results are included in the main body of the dissertation. As I mentioned, LLA incorporates the class distribution of both labeled and unlabeled sets to effectively mitigate class imbalance. To verify this, we trained the proposed algorithm on the imbalanced and imbalanced settings and examined the degree of logit adjustment lambda for each class. First, when both labeled and unlabeled samples are imbalanced, we see that the logits from majority classes are adjusted much more than those for minority classes. This indicates that LLA is learning to mitigate classifier bias. When the label set is imbalanced but the unlabeled set is balanced, majority classes logits are still adjusted more than minority classes logits, but the difference is smaller than the fully imbalanced cases. This allows that LLA incorporates the unlabeled set class distribution when learning the adjustment degree. Finally, when both labeled and unlabeled sets are balanced, the logits for all classes are adjusted to a similar degree. Comparing this to the orange lines confirms that LLA also incorporates the label set class distribution when learning the adjustment parameters. As I mentioned earlier, using EFCC increases the density of minority class clusters in the representation space, improving separability. To verify this, we selected the two classes with the most training samples and the two classes with the fewest, and plot the TSNE of their test set representation from Cipher 10 LT. The left figure shows the representation learned without EFCC, and the right figure shows those learned with EFCC. Blue and green points represent minority class samples, while red and yellow points represent majority class samples. In the left figure, minority class samples are very sparse and often overlap with majority class clusters. In contrast, in the right figure with EFCC, minority class samples from denser clusters and fewer minority classes overlap with majority clusters. These results confirm that EFCC effectively densifies binary class representations in the feature space, enhancing class separability. To demonstrate the significance of each component in our proposed algorithm, we conducted an evaluation study. When LLA is not used during training so that store labels are not refined, we observed a significant drop in performance. Similarly, when LLA is not applied during testing, so that class predictions for tests that are not refined, performance also drops noticeably. Additionally, omitting EFCC during training leads to a meaningful decrease in performance. These results confirm that each component of our proposed algorithm contributes meaningfully to its overall effectiveness. Thank you.